Hello, this is the last video for our short series on braid groups. For this last video we're going to talk about the topological kind of underpinnings for equivalence of braids. In the first video we asserted two braids are the same if you can move the strings around without them intersecting, but we can make this a little bit more formal using the notion of homotopy. So the notion of homotopy I'm using here is closer to the notion found in standard algebraic topology texts such as Hatcher, where the study of braids definition is slightly different but still equivalent. So we're going to say formally, between two continuous functions f and g from a topological space H, so in this topological space X, the rule is H is going to map the topological space X Cartesian product with the closed unit interval to another topological space Y. Y is another topological space. But the rule here now is for it to be a homotopy between f and g, we require that h x0 is equal to the original function f of x, and h applied to x at 1 is going to be equal to the second function g of x. So we mentioned functions here. These x's don't necessarily need to just be paths. They could be any number of surfaces. So for example, I have here these continuous functions. We might imagine this kind of sphere to start, and each arrow along the way is going to kind of give us a possible homotopy between them. We might imagine between these first two, we're taking the sphere and we're kind of squishing it into this pill type shape. And then in the second homotopy here, we're taking this pill, we're squishing it down to a smaller sphere. Maybe in this third step we shrink the sphere. Fourth step we shrink the sphere even more. And finally we turn it all into a point. These are all still continuous, so we're okay with squishing the sphere down to a single point and losing some information. It turns out that the composition of homotopies, provided you rescale the interval from 0 to 1 appropriately, is going to still give a homotopy. It turns out that as such we can come up with a notion of homotopy equivalence. So the idea of homotopy equivalence is we would say that two functions, specifically continuous functions, are homotopy equivalent or, if you'd rather, homotopic if and only if there exists homotopy H mapping f to g with all the properties we just described. It's going to act like a kind of smooth movie connecting these two functions. So an example that is maybe a little more classic is you might imagine you have alpha as this first function. It's describing the path from this base point here, maybe we call this point A, to this base point over here, maybe we call it B. And at time t equals 0, we might say h of x, comma 0 is equal to alpha. However, as time goes on, we're going to move closer and closer and closer to beta, continuously kind of dragging the string path along. And then finally, when we reach time equals 1, we get h of x1 is equal to beta. hence these two paths are homotopic. We can kind of find a movie that stretches one path into the other continuously. There's no cuts, tears. We aren't removing the path at any step of the way. We're just doing small, gradual changes until it turns into the other path. This idea is going to give us the idea of ambient isotopy. We have to be careful using regular homotopy because regular homotopy allows us to shrink an entire path down to a point, which is not something that we would want with our braids. However, if we consider the surrounding space that our function is, then we can define ambient isotopy. So maybe we will call this F. So if we let N and M be manifolds, which is a special type of topological space. It's one that's, I'm going to say this in quotes, relatively smooth. And we let G and H be embeddings of N and M. Then the continuous map, I'm going to be careful and say a continuous map because this isn't necessarily unique. A continuous map F, which is going to map from M, Cartesian product with the closed unit interval, into itself, is an ambient isotopy if f of 0, which is going to be the same as if we take f of x comma 0. We're using this notation for convenience. But f of 0 is the identity. It doesn't change the underlying space. Then if we take f1, which is f of x1, but instead of applying all of the possible points in this space, we specifically apply this only to G. Then we want this to spit out H. Further, we require each f sub t, so at each step of time, the corresponding function is a homeomorphism from M into itself. So what do we mean by homeomorphism? We mean a continuous function that is also invertible and also has a continuous inverse. So for example, with our braids, we might think of the braids, these red lines, as being the manifold N that's embedded in this cube M. So between these first two, you might notice that this little bit of string kind of gets pulled back up. We don't have a braid at this step, and we're okay with this. We don't necessarily need to have braids every step of the way for ambient isotopy. But notice nowhere along the way is there any kind of intersection. Between the next two steps, we might notice that this little bit here kind of gets pulled tighter. And then in this last step, this bit that's jutting up and comes back on itself is pulled back down, so we end with a braid. So if this is braid beta, this is braid beta prime, we would call this an ambient isotopy because each step of the way we make a small change. We still have homeomorphisms, meaning that the braids never cross over themselves, and the underlying space is still preserved. We don't shrink everything down to a point. Now, with our notion of ambient isotopy, there's one additional notion. It turns out that this is equivalent to the one we just discussed. But if we want to restrict this to braids, we might add a few restrictions. So in addition to the ambient isotopy, we're going to add the restriction number 3, that at each time, t, we might require that F sub t restricted to the initial braid. I believe that I called it F in the last one. So to keep the same notation, restricted to F is a braid. Now, without proof, I claim for braids the S isotopy and ambient isotopy are equivalent. So even though we don't have braids along the way, it turns out that won't matter as long as you pull the strings taut at the end. And geometrically and physically this makes sense. If I have string, I'm allowed to kind of twist it and tangle a little bit as long as I don't change the ends. And as long as I put it back, I'm not really changing the underlying structure of the string braid that I set up. That's all for now. If you'd like to read more, I suggest reading the book A Study of Braids that I linked in the description. It goes into more detail about some of this topology and isotopy of braids. It also has a lovely section about homotopy braid theory where you allow braids to self-intersect because there are some interesting properties that are preserved there. Thank you.